Good morning, Chris Potter. Today is December 27th, 2016. Today's presentation, possibilities regarding the brown dwarf's position. A physicist's thoughts. Let's begin. In this article, I am going to discuss the possibilities in estimating the position of the brown dwarf in our solar system. Figure 1 on the left shows an image of an object that fits the profile of the brown dwarf. It looks like an illuminated, fast-rotating cloud of gas. The brown dwarf is an old star that has converted all its fuel to iron and therefore was only able to emit infrared radiation. But since it has entered the solar system, it has gained energy and protons from the sun and has been able to start fusion reactions on its surface, thus becoming visible. The image on the right of figure 1 below is an Hi2-SREM-A image of the brown dwarf. Notice that both images show that the brown dwarf has a small circular center. This is probably where there's an opening in the ionized iron cloud surrounding the object through which the actual surface of the brown dwarf can be seen. Now remember, this is the baffle that NASA conveniently has positioned deliberately to hide the object of interest, which appears to be right here. Figure 1, left, object to believe to be the brown dwarf seen in Earth's night sky, and right, brown dwarf in an Hi2-SREM-A image. Now, since the Stereo A spacecraft can keep the brown dwarf within its field of vision all the time, whilst essentially following Earth's orbit, it suggests that the brown dwarf is in an orbit around our sun. Calculating its orbital radius is not easy. We need more information. However, new information has recently become available. Notice that the object on the left, on figure 1, which is from CosmicArtifactResearch.com, is seen in the night sky since there is a black object around it. The fact that the object is seen in the night sky means that it's beyond Earth's orbit around the sun, and this is illustrated in figure 2 below. If the brown dwarf position is inside the Earth's orbit, it will be seen in the daylight sky. Sun, brown dwarf, Earth. Very simple. Second option, if the brown dwarf position is outside Earth's orbit, which is what we are saying, it will be seen in the night sky. Sun, Earth, brown dwarf. Figure 2, illustration of fact that the brown dwarf has to be outside of Earth's orbit in order to be visible in the night sky from Earth. Now, some additional data has become available regarding a reversal in the direction of the solar wind, also called a magnetopause reversal. This reversal happened on the outside of Earth's orbit around the sun and has happened twice in 2016. Very conveniently on April 23rd, 2016 and October 14th, 2016. We have mentioned a 6-month cycle of these astronomical bodies that follows that theory very closely. Figure 3 shows the direction of the solar wind before the reversal occurred on October 14th. The direction of the solar wind is given by the direction of the arrows in the image below. Figure 3, diagram showing the solar wind velocity defined by the black arrows on October 14th, 2016. The little black and white circle represents planet Earth. The sun is to the right and the solar wind direction is to the left. Now in figure 3, the sun is to the right of the image and the solar wind points in the expected direction, i.e. to the left. As defined by the direction of the black arrows in the image. Now in figure 4, we see that all of the arrows on the right hand side of the Earth are now pointing to the right. Figure 4. Diagram clearly showing the solar wind velocity defined by black arrows on October 14th, 2016 at 2:28 Coordinated Universal Time UTC. The solar wind direction to the right of Earth is now in the reverse direction, or to the right, as indicated by the direction of the arrows. Figure 5, solar system scope view of the solar system on October 14, 2016 at 2:28, showing that if the Earth passed between the sun and another star, the star would have been in the Pisces constellation. All right. There are several ways that this solar wind direction reversal can be interpreted. The first and simplest is to say that the Earth passed between the sun and another star, which produces its own particle flux and was therefore able to counteract the sun's particle flux or solar wind. If that's the case, this object would be in the constellation Pisces, as shown in the solar system scope view from October 14th at 2:28 in Figure 5. Figure 6, shows that magnetopause reversal, of April 23rd, 2016. It's below. The reversal is not as dramatic as the October 14th, 2016 reversal, suggesting that if the same object caused both reversals, it must have been further away in April, meaning it's closer now in October. However, there's actually no way of knowing for sure that it was the same object, but we can consider the possibility that it is the same object and see what conclusions we actually arrive to. Figure 6 diagram showing the solar wind velocity defined by the black arrows on April 23rd, 2016 at 5:34 UTC. Some of the arrows to the right of the Earth have reversed their direction. Now, Figure 7 below shows the Figure 7 below shows the solar system scope view on April 23rd, 2016 at 5:34. Now, we see that if the Earth passed between the sun and another star, thus causing a reversal in the solar wind direction, that this star would have been in the Virgo constellation. Figure 7, solar system scope view of the solar system on April 23rd at 5:34, showing that if the Earth passed between the sun and another star, the star would have been in the Virgo constellation. We cannot be sure that the same object caused both magnetopause reversals in 2016, but we can consider the idea. If it is the same object, it must be outside of Earth's orbit and is therefore unlikely to move fast enough to encounter the Earth on April 23rd and then again on October 14th, a time interval of 173 days. Okay? Now, but there is the possibility that the object was not on the outside of Earth's orbit both times, but that an alignment between the sun and the Earth and this star caused the reversal. In that case, the magnetic flux change caused by the Earth's alignment with the sun and this star could be enough to cause a reversal in the solar wind direction on the outside of Earth's orbit. If that is the case, the star would be outside the Earth's orbit for either one of the times and on the opposite side of the solar system the other time. Since the effect is stronger on October 14th, we're going to assume that it was closest to Earth at that time and on the other side of the solar system on April 23rd, both dates of 2016. This is illustrated in Figure 8 below. Earth's position on April 23rd, 2016. Earth's position October 14th, 2016. If there's a brown dwarf star, these would be their supposed positions on April 23rd and October 14th. Figure 8. In the case of the same star producing the magnetopause reversal on April 23rd and October 14th, 2016, the possible sun, Earth, and star's position on both days are illustrated above. Now, if the star had not moved at all between the first reversal event and the second in 2016, we would expect the period of time between reversals to be half the orbital period of Earth, which is 365 days. So we would expect the period of time between the two reversals to be 182.5 days, but instead the time was 173 days. This means that the star moved by an angle equivalent to 9.5 days on the Earth's orbit. In other words, the star's angular displacement was calculated below. Theta is equal to 2 pi 9.5 days over 365 days, which is equal to 0.1635 radians. And a time period of 173 days, so its angular speed would be, equation 2, omega is equal to or 0.1635 radians over 173 days. Then, assuming that the star is orbiting the sun, we can, from the angular speed, estimate an orbital period, which is equation 3. T is equal to pi over omega, which is equal to 6.65 times 10 to the power of 3 days, which is equal to 5.74 times 10 to the power of 8 seconds. Get that? I did. All right, and from the orbital period, we can use Kepler's third law to estimate the star's orbital distance from the sun, which is equal to the cubed root of gm over 4 pi squared times t squared, which is equal to 6.9 AU, or astronomical units away. That's how far it is away. Where g is the gravitational constant and m is the sun's mass. If this star is the brown dwarf visible in SETI images, then its orbital distance from the sun would place it between the orbit of Jupiter and Saturn, and closer to the orbit of Jupiter than to Saturn, since Jupiter's orbital radius is 5 AU and Saturn's is 9 AU, because the calculation is 6.9. A physicist's thoughts, possibilities regarding the location of the brown dwarf. Have a great day. Thank you again. Bye now.